G'day and welcome to Dr. Drew's Earth and Space Australian Curriculum, version 9. Hope I can share some things today that will help you in your teaching. So, what is in the version 9 of the curriculum for Earth and Space? Well, in Foundation, there isn't. We can live with that. It's already a pretty crowded curriculum. But you're still able to teach great science skills, observation. Look at the sky, look at the ground, tell me what you see all around. So it's there. It's there. In year 1, we start to focus on weather, days and seasons. So learning how to dress appropriately and habitats, migration, storybooks, lots of stories and narratives that you can use to talk about season, even the ugly duckling, for instance. But what I do ask is you avoid the disconnect between science and life. And by that I mean go outside. Don't talk about the weather if you never look up at the sky. So much of our educational heritage comes from Northern Europe and it just doesn't fit the places that we're teaching here in Australia. Actually look at the sky. Actually talk about and research local wildlife. One thing that often surprises kids is the moon comes out during the day. So keep a moon diary. Actually look at the sky. Actually go outside. There are not 4 seasons in most places of Australia. Not at all. Perhaps your kids can help you name what seasons they think belong in the year. Because all your conclusions in science need to be evidence-based. So get your kids to go outside, look at the earth, look at the sky, tell me what you see all around. And here is something I saw on CQU, Bundaberg campus, looking around in that scene. Can you spot the frilled-necked lizard on the tree? There's that little guy just hanging out there, chilling out in the morning sun. There's things all around. Another great idea is a sky diary. You can get your kids for 1 month at about the same time every day to go out and look at the sky and tell us what you see. Clouds, sun, stars, what is in the sky? Can get them to use some of their new words here in grade 1. So we're talking 6-year-olds usually. This is something AI whipped up for a sky diary every day for a month. It can be tricky to draw the sky because it's kind of round shaped. So the middle is it's directly straight up, and I'm imagining you're at a school between the classrooms at one end and the school flags sort of opposite, so you can stand in between those 2 points and look directly up and get the kids to describe what they see. Some days it's all blue, and some days the clouds are puffy and white, and sometimes the clouds are wispy and feathery. And sometimes you'll see the moon. So, yeah, actually look out. Actually look. Look at the world. So, year 2, sun, moon, planets and stars. So now we talk about the nighttime sky, and that's a great time to get some astronomy happening. Maybe get out the telescope, or I will admit lots of videos on the internet are a lot clearer and better presented than what you can see in the sky. But we're talking about the planets. We're talking about these little guys. I designed an activity, and the hyperlink's right there, where I'm imagining the average 7-year-old's about 1.4 meters, give or take, maybe a bit less. But this is how big the planets are if their body was the sun. So you can see the sun doesn't look very big in the sky, but it's actually huge. 1 million Earths can fit inside the sun. So these are little tiny air modeling, air drying clay: Mercury, Venus, Earth. Wait a second, they've got them in the wrong way. Mercury, Venus, Earth and Mars. And yeah, that's how big the close planets are. You also get to talk about the moon, and the moon's such a fun topic to talk about. We'll get to that in a sec. Here's some of the larger planets: Neptune and Uranus, if you want to use the original pronunciation. You know, the scientist who found that star, the furthest out, sorry, second furthest out, Uranus, Neptune. Wanted to call it George after the king, but the scientists got together and had a vote and said, no, we're going to call it after one of the Greek or Roman gods, just like all the other planets. So that was fun. Imagine having a planet called George. Bah, yes, the moon. What we have here is a picture of the moon, which is a near side. You see, the moon always faces the Earth. It spins, but it spins at the exact proportion of its rotation and revolving. So one side always faces the Earth. We only see one side. The other side is called, well, they used to call it the dark side, but that made no sense. It was only dark in the sense that we didn't know what was on there. But it was just as well lit as the near side. We finally got the astronauts and sent them in the spaceships in the 1950s and took some photos of the far side of the moon and found it was quite interesting. These little dark patches, they're called the Mar, which was Italian for sea, because they weren't too sure when they were first looking through the telescopes in the 1700s what those dark patches were. Could they be seas of dark liquid? But no, they're actually enormous plains of basalt rock. Basically, when the moon was still a great big ball of lava, just as the moon creates tides on the Earth was creating tides on the moon. And some of that lava came out to form these great big flat plains, whereas the far side of the moon wasn't having that effect happening. So you've got these beautiful, beautiful craters on the moon because there's virtually no atmosphere on the moon, there's virtually no weathering. So if you get an asteroid or crater gets formed, it can stay there for potentially thousands of years, millions of years. The footprints of the astronauts on the moon are still there and may be there for a very, very long time. So, fascinating thing, the moon. One side faces us, one side never does. I really do love the moon for all it can do. You don't need to go into this much detail because there's so much about the moon. Its orbit is tilted at about 5 degrees, which means sometimes the eclipses, when the moon gets in the way, sometimes the eclipses are in different places. Sometimes the shadow of the moon doesn't show up on the Earth at all. Not only that, the moon's orbit is not a circle. Orbits in space aren't circles, they're ellipses. But even then, the ellipse shifts every time you have an orbit. And the moon's quite obvious. It's called the precession. All the planets do it. Mercury's the most obvious. But the moon's precession is also very obvious, and that's another reason why the moon's in slightly different places all throughout the year. Also, the moon is not small. It's smaller than Earth, but it has about 1.5 times the surface area of Australia. It's pretty big. And you do have moonquakes as well. They experience them when they're on the moon, just rocks shifting and moving about some places. And yes, here's your classic picture of what causes the different images. Though the moon appears to change, it doesn't change shape, but different parts of it light up, and that's why we see different things. The new moon is when you can't see it at all, and the full moon is when the moon and the sun are on opposite ends of the sky. It's so amazing, just so amazing. We're very lucky in this universe to have a moon so large and so close. We don't think too many places in the universe might have this lucky situation. What's even more incredible, the moon is 400 times smaller than the sun, but the sun is 400 times further away, so they look the same size, just about. That's why eclipses work, because the moon can get right in front of the sun, well, the image of the sun, and create these beautiful, beautiful eclipses where all you can see is the atmosphere of the sun coming around the edges. Special things, but you best not look directly at an eclipse. As they say, some of the colours coming from the sun are invisible. And even though the visible light during the eclipse is not very bright, some of the other colours are just as bright as ever. And they will damage your eyes. So you need eclipse glasses, or even easier, just look at the shape of the shadows during an eclipse. All the shadows are different. Really fun. There's an eclipse every few years, at least partially, wherever you are. Earth and Moon. Earth is lucky to have such a wonderful companion. So, some more stuff you can work on is sundials. Sundials are really fun. This is an equatorial sundial, which I found quite useful. The kids are just, homeschool kids here displaying their great works of art, simply put together. Sundial's really interesting, and it's a way to put shadows to work. And of course, there's lots and lots of Indigenous connections. I hope you've heard about the emu in the sky. There are some really good links in the PowerPoint presentation on this. This is Uluru, Ayers Rock in the centre of Australia, and a really, really very good picture of the Milky Way. Now, as you know, the Greek astronomers, those who are the great progenitors of Western science, joined some of the brighter dots and imagine there were images, that gods had placed images and messages up in the stars. I just find it fascinating that the Australian Aboriginals have looked at the same stuff, same place, and they joined the dark patches. They said that's a thing, that's a something. It's not a nothing. Complete opposite. Complete opposite. They said, if you look at the sky in certain times of the year, when you get the view just right, it's like there's a giant emu that sort of takes up the whole sky. And various different cultures and nations would apparently use that for helping them to know what sorts of fruits and vegetables and other sources of protein were available at different times of the year. So, worth your time looking into. Indigenous astronomy, some very, very interesting things have been discovered. Let's skip ahead to year 3. So we're talking the 8-year-olds now, and quite fascinatingly, we suddenly take a deep dive right into rocks. I really hope you like rocks, because rocks are fun, rocks are absolutely fascinating. You're probably wearing a rock right now in your jewellery or your wedding ring. So it's like the mining community got a hold of the national curriculum and said, hey, come on guys, you can't cut us out. We got stuff to share here too. It's true, Australia relies very much on our natural resources and on mining. So what can we do? It is interesting. Soils, rocks and minerals, also in year 3, during the biological sciences, you're talking living and non-living. So this is a place to reflect on that outcome from a previous or future term. Growing crystals is a lot easier than you'd think. There are some fun crystal activities. You can grow them yourselves. And they're a really good way of demonstrating how the igneous rocks are formed. Then there's sedimentary sculptures. I really do love, the 3 families of rocks: igneous, sedimentary, and metamorphic. You can look up recipes and cook sugar in each of these ways to illustrate how these rocks form naturally in the environment. So I also think it's valuable collecting rocks around the school. Now, it's a matter of debate whether you should put them back when you're finished with them, because that's where they come from, so that's where they belong. That's the land. And on that topic, heaps of First Nation stuff on rocks and crystals. We've got ochre, for instance. You may need to get your Indigenous person at the school, may have to have special permission to access ochre and, get drawing and painting the kids. Really good fun. Reminds me of my time up in Tennant Creek. Incredible place, incredible stories. This is a really easy crystal thing. These are copper sulfate, and I did these myself, copper sulfate, straight from a hardware store. It's a plant fertilizer. Mix it in hot water and dissolve it until no more of it will dissolve. Then I poured it in a plate, and by the next morning we had these great big crystals of copper sulfate. Salt and sugar also work. This is from the classic activity where you get a put some salt or sugar in hot water and stir around and keep putting in salt or sugar, not both, one or the other, until no more will dissolve in there. Then you let it cool back down slowly. And this is where you put a stick with a string dangling in there. It's just so fascinating because as the liquid crawls up the string, the top of the string is where the crystals form quickly. So these are irregular crystals. Exact same things happens in nature. If you've got lumps and lumps like that, the crystals could have formed rapidly, sometimes within minutes, sometimes within centuries, but they form quickly for that crystal. And down the bottom you get the crystals that form slowly. So these have time to form regular shapes. The exact same thing happens in nature with quartz and all sorts of other materials. The longer they take, nice and slow, they can develop really solid, noticeable crystals. And there's so many materials. Crystals form every chance they get in nature, just about. It's astonishing how many things are crystals. So Year 3 rocks is really fun. This is my sedimentary sculptures activity, telling a lesson. The further down you go, the further back in time you usually head. I mean, rocks can get squished and twisted, and sometimes they can even flip over upside down. But usually, as the different layers form, it's like looking back into the past. Maybe I should have stuck a little dinosaur fossil down here. And I like to keep the bottom one red because the rocks at the bottom, they're so hot under so much pressure, they start to turn into a liquid. Now, it's not splashy. Well before you get to splashy liquid, you have treacly liquid. It's called the moho discontinuity. As you dig down, the further down we go, after a few kilometers, we can't dig down anymore because the rocks start to like incredibly, unnoticeably slowly, just sort of slowly fill back up the gaps that we've been digging, and they squash the drill bits and prevent them from digging any further. Which is kind of a useful thing, because if there is much pressure under the earth, it takes a lot of pressure before it can push through those treacly layers and start to explode out on the surface to create volcanoes. But yeah, Year 3 rocks is just absolutely fascinating. So much fun stuff. And if you can learn to love rocks and crystals and gems, you're doing great. After all, we need minerals, and they come out of the earth. Year 4, water. This is an interesting turn for the curriculum to take, but I shall allow it. Precipitation, evaporation, condensation. Some really great activities: making clouds, getting kids to make vortexes. From these vortex bottles here, you can get a special connector or just tape them up together. You can use glitter or something more biodegradable, such as dirt, just out of the playground to show how the water spins. Just like the planets, it's fascinating. The water spins fastest near the middle and slower around the edges. That's what the planets do too. And making clouds, this is one activity where surprisingly easy to do, but uses fire and dust, so you might want to have a grown-up here to help your kids out. So with this homeschool group, you put a little bit of dust in that bottle here, then a little bit of water, close it and shake it, shake it, shake it, shake it. And then, this is the trick, you've got to heat it up. The way we heat it up is just by squishing it. Compression. By compressing it, it gets a little bit hotter. And then, when you release it, it suddenly drops colder. And that results in the formation of a cloud in the bottle. Look at those. Oh, 9 and 10-year-olds creating clouds in a bottle themselves. So, all you need is the ingredients of a cloud. Tiny little cloud seeds for little tiny bits of water to form on. Helps kids realise how rain helps clean up the air and get all tiny bits of dust, pollen and dirt out of the air. Year 4 water is really fun. It is an absolute excuse to play with siphons and to get soaking wet. So I hope you enjoy Year 4 water. It's great. It's really fun. I did want to make a point about the water cycle. Okay, can anybody guess here, what is my problem? What is my problem with this water cycle? It certainly looks like a cycle. It makes it look like the water comes out of the lakes, goes into the clouds and then drops on the mountains. There's so much wrong with that. It's vastly oversimplified. You see, does it really only rain on mountains? It rains everywhere. This is a much better water cycle. It shows you that the water can come up from evaporation, from transpiration, from sublimation, even as ice turns directly into air, joins the air as, water vapor. And precipitation can happen all sorts of places as well. Out over the rivers, it can be on top of the trees, it can be on top of the mountains. So yeah, please please don't do that other water cycle. It's too simplified, right? It's like the water cycles. Maybe we should call it that. Is that what's going to work? Perhaps it is. So yeah, transpiration's fun. You just put a little bag over a tree's leaves, tight. After about an hour, there's a little puddle of water in the bag, because trees bring water up out of their roots, bringing the minerals up out of the ground, up toward their leaves, and the water evaporates and the minerals are able to stay in the leaves so the tree can grow. I like that about science. You can't tell one thing about Earth and space without telling things about biology and physics and chemistry. It's just all interconnected. So, and then we have Year 5. Year 5 is about weathering, erosion, transportation, and deposition, which has the potential to be awfully boring. But I think it can be a lot more fun if we remember that it's pretty much about disasters and how things can change slowly and suddenly. It's true, we're not talking earthquakes. But deposition is an interesting one. Like when a glacier is sliding over one area, it drags the rocks from the top and places them somewhere else. We found fossils, for instance, that didn't look like they should be there until it was pointed out that there was a glacier there 100,000 years ago. So Year 5 can actually be really, really interesting. And you can do some really fun activities there. Like, I've seen a few, you got to know your kids and know what's going to work well for them. But, getting a little collection of sand, like half a cup of sand, and having competitions with the kids who can blow away the sand with the straw the fastest. You want to organise that because sand's going to get in people's eyes. But there are some kids who just won't connect unless you give them some sort of very physical, very, very hands-on, kinesthetic challenge. And it helps to make what has the potential to be an awfully boring year in the science, earth and space curriculum. Makes it more interesting and purposeful and dramatic. So please enjoy the national curriculum and do things that are going to be fun and challenging for you. Another fun erosion activity could be you get like a cup, and you could get chunks of dirt and rocks and shake it. Why do that? You can get an actual cookie. Just get a cookie and shake it up, and then get the kids to observe carefully what's happened to their cookie and see how it breaks down around the edges first and such. Tell them that the skill they're learning is observation, that you want to test their observation skills. And then, of course, you might choose to let them eat the cookies. So have some fun with Year 5. Weathering, erosion, transportation and deposition. Slow and rapid changes to the Earth's surface. So real potential there. Some good stuff. There we go. Another activity, you can place chalk, limestone chips or eggshell pieces in vinegar and compare with water to experience chemical weathering. And that's an interesting one. It takes sort of 10 minutes to an hour, depending on the level of the strength of the vinegar you're using. So if you prepare the kids well, that they're going to have a slow experiment, they can begin to experience chemical weathering. That matters because then you talk about some of the sculptures that you might have in town or the buildings, the really beautiful old buildings. And you're like, if the acidity level of the rain keeps up because of, we're not managing pollution properly, it's going to start damaging the building. So, keep the science practical. Let them know there's things they can learn. Make a cake with layers to demonstrate deposition and then eat it. Play ping pong balls through a straw to demonstrate wind erosion. So yeah, lots of fun activities. Please make year 5 interesting. Moving on, let's try year 6. We go back to space. Earth in space, axial tilt, seasons, night and day, and gravity, etc. So here's a picture which I found problematic, which attempts to explain why we have seasons. And you know how they're like the Earth is on its axis. And I ended up, as a kid, I thought it went like that, and then it wobbled on its axis as was spinning through the year. It sort of wobbles backwards and forwards. Despite having seen multiple pictures like this, which are much more accurate, the axis upon which the Earth spins is very, very stable. It shifts minimally throughout the year and throughout the centuries under most circumstances. So yeah, it's summer in the northern hemisphere and it becomes winter in the summer hemisphere by the time the Earth has gone all the way around. The axis stays pointing to the same direction all the time. And in a way, I appreciate this is more a cartoon version because it's obvious. It's easier for the kids to realize for themselves that this is just symbolic. Ask the kids what's symbolic about this image. Well, there's no big words in space. And also the sun is so much larger. I mean, if on this scale, the scale in space is really difficult to represent. But I do think something bothers me about the primary school curriculum, and I wonder where your professionalism takes you. I'm like, where is climate change discussed up to the 11-year-olds? Where are the fossils and dinosaurs? Kids love dinosaurs. Why aren't we talking dinosaurs in primary school? You've got some changes to suggest, should we? Can you fit them in? Do you think they belong? The fossils certainly do belong in what we currently have in the year 3 curriculum. We can certainly talk about them there. Are we avoiding confronting issues? Very sensitive religious and cultural beliefs. Perhaps that is so because these topics are dealt with in high school. Very quick rundown. Year 7 space again, eclipses, seasons and tides. I'm not too sure how to make that reasonably boring, but moving on. 8 is plate tectonics. I think that's very valuable for kids to learn. So we're talking about rock cycles, rocks, maybe fossils here. Then we get to year 9, we're talking atmosphere. Right now we're finally talking carbon cycle, which is very, very much global climate change, photosynthesis, respiration. So year 9, we're tackling the big issues by then. And by year 10, we finally get to Big Bang and the history of the universe. And what's particularly fascinating is, we've got the physics curriculum, chemistry and bio. They all have to stand on their own, but it's like Earth and space kind of squeeze into their own year. But by year 10, they really do become one. The whole Big Bang history of the universe, history of our planet Earth, really ties in Earth and space. So we'll talk a bit about that idea. Definitely a place for global climate change. So in a page, you don't need me to give you a bunch of lessons. There are millions available online. You need the groundbreaking theories that tie together this body of knowledge so that you can access deeper understanding for yourselves. So let's take a deeper look into one of the big ideas, and there are lots of them. It's a weird phenomenon in the history of science where the very edges of what we know sometimes fall back in and overlap over each other, and we discover that one great theory can explain 2 previously very disparate observations in nature. How it all began. Let's talk about the Big Bang Theory, which is one of those incredible theories which helps tie everything together. Okay, but what do you know about the Big Bang? Who said it? Who came up with that idea? And what did he or she use to convince us? Where's the evidence there? Another big idea, which is worth your time, is spinning in space. Who says? Too long to list. Copernicus, Tekla, Brahe. I mean, let's face it. It doesn't feel like the Earth's moving. What evidence do we have? Why would we ask the kids to believe in something that is so profoundly different to their everyday experience? A lot of people say the Earth is moving slowly, but as I've said, it's spinning very fast. On the equator, about 1,700 kilometres an hour. Race cars do 300. So we are going very fast. But the room and the air and all of it's going along with us, so we don't even notice it. So what did it take to convince the world, convince humanity the world is spinning in space? And tectonic plate theory. That's a really good one to get to. Very worth learning about. It's such a very interesting theory. It used to have a different name too. But these big ideas really do help us. Starting with the Big Bang Theory. Oh, it's an incredibly important and incredibly complex theory at this point. So let's go back to when it was a little bit simpler. And thank you to Wikipedia for helping do the outline for this. The big question has been, how did the universe come to be? We used to, when we first developed telescopes in the 1700s, scientists like Leonardo were looking at Jupiter and they're like, there's these 4 dots and it's like they must be little things circling Jupiter. So not everything goes around the Earth. Some things go around other things. So they developed the idea of the solar system and maybe stars have other planets going around them, perhaps. And in the last 20 years, we developed the technology to actually detect planets going around distant stars. But as we looked further out, we saw these little blotches out beyond the stars. Well, what are those blotches, little nebula? Well, what could they be? So how the universe came to be? Well, one theory was it's always been. It's called a steady state. Albert Einstein loved the theory. The idea is the universe has just continued to exist and may forever do so. But another theory began to grow. It started at the central point and it continued to grow. So how did that come about? Well, forgive my pronunciation, it's French. Georges Lemaitre proposed the infrared recession of nebulae was due to expansion of the universe. You see, as the telescopes go better, we began to see those little distant clouds that are between the stars. He noticed that if you measure the light really precisely, it's like it's shifted a bit towards the red, and that's actually quite easily explained if those tiny little blotches are moving away from us. That would cause their light to shift towards red. It would stretch out the light waves. So they actually, around about that time, decided the little nebulae, little blotches were actually other galaxies. They weren't stars. They were clusters of millions of stars. It was just mind-blowing how incredibly large the universe seemed to be. But he did a bit of maths there and thought to himself, well, if everything's flying away, maybe back in the distant past it was all crunched together into some sort of primeval atom. Maybe it was infinitely small and just sort of grew out from that point. But still, in the 20s and 30s, steady state universe was the preferred theory. And what's really interesting, some people complained that saying that there was a beginning of the universe was like importing religious beliefs into science. It didn't help that Lemaitre was a Roman Catholic priest, which is an interesting, fascinating part of this story. So after World War II, both theories were being fought over, being worked on very, very, very intensely by scientists who were for and against both models. So Fred Hoyle's steady state model and Lemaitre's, well, he didn't call it the Big Bang Theory. As a matter of fact, Fred Hoyle was the one who called it the Big Bang Theory. He was mocking it during a radio interview. And the name stuck. I don't know what to think of that myself. So the observational evidence kept coming in, and it began to look like Big Bang was winning. The further out in the universe we looked, the more red-shifted the other galaxies are. So they're moving away even faster, which is what we would expect to see if it had exploded from, I don't want to say central point, but exploded from a point in the past. But the big winner was CMB. Okay, let me get to that. American cosmologist Ralph Alder predicted CMB when he was working with Robert Herman and George Gamow. The theory is, right, if the universe began with a great big bang, it would be like lightning and then there's thunder. There should be something, a remnant of an explosion that big. And according to the mathematics, there should be this essentially microwave hiss in every direction of the Big Bang having cooled down to about 4 degrees above absolute zero, which is as cold as the very, very depths of space appears to get. And if they could find that cosmic microwave background radiation, it would provide very compelling proof to support Big Bang, not steady state. But it was found shortly after by accident. Okay. Two researchers, Bell and Telephone Laboratories, were creating a radio receiver and were puzzled by the noise it was picking up. It came uniformly, all over the site, every direction. They're like, what is this hiss? It's really annoying. And then both teams quickly, Herman and Gamow were like, we can explain it. Yeah, we know what that is. And like, oh, you know what that is? Yes, it is. So they both published. Sadly, only Penzias and Wilson received the Nobel 78 prize. Not the guys who came up with the idea, but the guys who actually who detected it. I don't know if that's fair or if they should share. I'll let you decide for yourself. But how extraordinary that the theory and the evidence turned up almost the same time through completely different lines. It is extraordinary. Here's a picture of the horn antenna, which they were using to detect the microwave energy, radiation, because it is electromagnetic radiation, which is essentially a different color of light. Here's a visible light. Microwaves are just off to one side. There they are. There's our microwaves. This is not to scale. Not at all. But you can see the waves of microwaves are somewhere between 1 centimetre and 10 metres. So, and there's a bit of overlap, bit of debate on when an ultraviolet becomes a soft X-ray or a electromagnetic radiation is simply amazing stuff. The wave that waves through nothing, that self-perpetuates itself through the entirety of the known universe. It's extraordinary. Could you imagine a wave the size of a building? You'd think it would knock the building over, wouldn't you? But it doesn't. There are times where it shines right through it, makes a brick look like glass. The radio waves go straight through it. That's why you can listen to the radio when you're sitting inside a car or a building, because they're like transparent glass to radio waves. So much to be. This stuff is just fascinating here. So the microwave background radiation was compelling evidence for the Big Bang Theory. And here is a picture, one of the more recent pictures, of the universal map of cosmic microwave background radiation. It makes it look like there's some really hot spots, but we're talking, I believe, millions, thousandths of a degree difference. So it's, accentuated in this picture. But it's fascinating that it is blotchy, and we're wondering why it would be. That's another question science yet needs to answer. Why are there subtle variations in the cosmic microwave background radiation? So many questions. So, evidence for the Big Bang Theory. The further away galaxies are, the faster they are moving away from us, like an explosion would. Faraway galaxies are further back in time, so they look noticeably different to the galaxies in terms of star composition and such. The leftover heat from that explosion, now 4 degrees above zero, is measurable in every direction. That's what we call the cosmic microwave background radiation. This last point has actually changed since I last got this slide ready. Heavy elements, such as beyond lithium, can only be naturally created in supernovas, which is a giant exploding star. And just this year, they recently found all the other heavy elements being created by 2 neutron stars colliding. So supernovas are not the only place where heavy elements are created. But yeah, it all continues to support that if the Big Bang created mostly hydrogen and helium, how did all the other elements, atoms, get here? And now we've found scientifically plausible reasons how they did. The age of stars that we can observe fits with what we know about the age of the universe. So yes, the idea is the universe is about 13.5 billion years, I believe, is the current best estimate. And time, space, matter, energy, all created in the Big Bang. A few problems with the Big Bang theory. Why is there more matter than antimatter? That's one of the questions we're trying to answer. Why does there appear to be more matter, more gravity than we need for the universe? Only 10% of it we can account for. Dark matter. It's probably not dark, but we call it dark because, like the dark side of the moon, we don't know what's there or what it is. And dark energy. How is the universe still expanding and not slowing down? So, lots of questions with the Big Bang, like all science. As I've been saying all the way through, so much to learn. When you answer a science question, and you do it well, you often end up with more questions than you started with. So here is a reasonably recent image of what the universe looks like, with each tiny, tiny dot being a galaxy unto itself. So this is just the visible universe. We don't know how far the universe goes beyond that, because as you may know, the universe is expanding and the edges are going away from us at more than the speed of light. So whatever's out there, even if light leaves that star or object or alien person's torch, it will never reach planet Earth. So we don't know what's beyond the edges of the visible universe. We're about 43, 46 billion light years away. Incredibly large distance. I'd love to know what's beyond there. Now, keep it in mind, all motion is relative. They don't feel like they're moving away from us at the speed of light. They probably feel like they're sitting still on their own planet, not moving very much at all. Science is fantastic, isn't it? You just got to keep an open mind and keep asking questions. It's the best way to learn. One misconception that a lot of people use for the Big Bang, say that it happened somewhere. No, the idea is the Big Bang happened everywhere. It created space. It didn't happen in empty space in order for the maths to work. The Big Bang created matter, time, space, and energy as well. So, mind-blowing, really. Before the Big Bang, there was nothing? No, we don't know this. We only know that our current understanding of the laws of physics break down about 13.5 billion years ago. We don't know what was before the Big Bang. There may have been a lot of things. Perhaps a big crunch, that's still in there with a shot, I think. So much yet to figure out. Which is cool, which is good. If you're comfortable with not knowing, you can really enjoy science, because there's still a lot we do not know. So what? So this is a CGI image of dark matter. We don't really know what it is. Multiple scientists over hundreds of years collaborated to create the ideas. We try to teach kids in a single lesson. Science isn't finished. All our atoms and molecules can be successfully explained by Big Bang cosmology. It's where the stuff all comes from. If you're going to talk Earth and space, you are talking the Big Bang. And I'll leave it there, just for now. There are many more questions for us to explore, many more things for us to find out. I know I'm certainly not done asking questions. How about you? I'll catch you around.